A traveller returns home after a long journey. The house he left still stands in the same place. The shape of the alley is much as he remembers it, and the afternoon sunlight entering through the window has hardly changed. His point of departure and his point of arrival are the same. But is the person who has returned the same person who once left? Probably not. The seas he crossed, the unfamiliar cities he visited, the people he met along the way, the things he lost, and the truths he discovered have all left something within him. The journey is over, but the changes created by that journey remain. Returning home does not mean reversing time. It means standing in the same place while carrying the path that brought you back. But does this apply only to human beings? Imagine a single, tiny electron travelling along two different paths and then returning to its starting point. Suppose its final position is the same, its velocity is the same, and all the surrounding conditions have returned to their initial values. Is that electron now in exactly the same state as it was before the journey began? The intuition of classical physics seems to say yes. If we know an object's present position and state of motion precisely, the route it followed in the past may appear irrelevant. Whether a climber approached a summit from the eastern trail or the western trail, we might say that the present state is the same if the climber is now standing at the same point with the same velocity. Quantum mechanics, however, gives us a startling answer. Even after a particle returns to its starting point, it may reveal a trace of the path it has travelled. Stranger still, this trace can appear even when the particle experienced no force during its journey. It is almost as if an electron, having travelled unseen along an empty road, speaks at the final moment through an interference pattern and tells us where it has been. Does the electron have a memory? Does space itself remember the electron's journey? Or is there some connection between particle and space that we have not yet fully understood? Today, we will follow this mystery. We will begin with the Aharonov Bohm effect, in which an electron changes even though it feels no magnetic force. We will then encounter the Berry phase and holonomy, through which a quantum state preserves the shape of a journey. Finally, we will ask how the IG, or information gauge perspective, might offer a new interpretation of what it means for the universe to remember. But one boundary must remain clear. The Aharonov-Bohm effect and the Berry phase are established parts of modern physics supported by theory and experiment. The information gauge perspective, by contrast, is a research hypothesis exploring whether a deeper informational structure may exist. We will not mix these two domains. As we begin our journey, we will distinguish carefully between known physics and ideas that still require experimental verification. Let us start with a very ordinary question. If something returns to the same place, does everything return to the way it was? Draw an arrow on a flat sheet of paper. Move it around the edges of a square while keeping its direction fixed. After completing the loop and returning to the starting point, the arrow points in the same direction as before. In the ordinary space of daily life, this seems perfectly obvious. Now imagine doing something similar on the surface of Earth. Begin at the North Pole and carry an arrow toward the equator while keeping it as parallel as possible to its previous direction. Move sideways along the equator and then return to the North Pole along another route. Although you never deliberately rotated the arrow, it may point in a different direction when it returns. No one secretly turned it. The difference appears because the surface across which the arrow travelled is curved rather than flat. The arrow returned to the same starting point, yet the curvature enclosed by its route remained as a change in direction. This gives us an important clue. Sometimes we cannot understand an object's change merely by looking at where it arrived. We must also know the path it followed and the structure of the space through which it moved. The effect of a path does not always appear as a push or pull experienced during the journey. The geometry of space itself can leave a trace, but this is still a story about a visible surface and an ordinary arrow. In the quantum world, something far stranger occurs. Imagine a device that fires electrons one at a time. We divide the possible route of each electron into two paths and bring those paths together again farther away. Because an electron also behaves like a quantum wave, the possibilities associated with the two paths overlap and create a pattern of bright and dark interference bands. Now place a long, narrow coil between the two paths. This device is called a solenoid. When electric current flows through it, a magnetic field is created. In an ideal arrangement, that field can be confined almost entirely to the inside of the coil, leaving almost no magnetic field along the outer paths taken by the electrons. From a classical point of view, the result should be simple. If there is no magnetic field where the electron travels, the electron should experience no magnetic force. Changing the field inside the coil should have no effect on an electron moving outside it. But that is not what happens. When the magnetic flux inside the coil is changed, the electron interference pattern shifts. The electron never passes through the region containing the magnetic field. Along its entire path, the direct magnetic force is essentially absent. And yet the electron behaves as if it somehow knows that the magnetic flux inside the coil has changed. This is the Aharonov Bohm effect. When we first hear about it, we may imagine that the electron somehow senses a distant magnetic field instantaneously. Modern physics gives a subtler explanation. Electromagnetism contains not only electric and magnetic fields, but also quantities known as potentials. In classical physics, these potentials were sometimes treated mainly as convenient mathematical tools for calculating the fields. After all, we can change the way a potential is represented without changing the electric or magnetic field that is actually measured. Does that mean the potential is merely an accounting device invented for our convenience? The Aharonov-Bohm effect shows that the answer is not so simple. Along the two possible electron paths, the electromagnetic potential leaves different traces in the phase of the wave function. The phases accumulated along the separate paths are compared when the electron waves meet again. Their difference then appears as a displacement of the interference pattern. What matters is not the value of the potential at one isolated point. Its local representation can be changed, but the relationship between the phase accumulated around the complete closed path and the magnetic flux enclosed by that path cannot be removed arbitrarily. What we finally observe is not a number attached to a single point, but a relationship created by the path as a whole. Nature seems to remember not the labels attached to individual points, but how those points are connected. At this moment, our picture of physical reality turns upside down. In classical intuition, a force changes an object's motion. If there is no force, there should be no change. But in the quantum world, even when there is no local force, the global structure enclosed by two paths can alter a measurable result. The electron does not peer inside the coil. Instead, when the quantum states evolving along the two paths meet again, the relationship between those paths becomes visible. It would therefore be misleading to say that the electron literally thinks or remembers. An electron has neither a brain nor a storage device. Here, memory means that a present result depends not only on the conditions at the particle's current position, but also on the complete path followed in the past. And this trace of a path is not restricted to electromagnetism. A quantum state itself can preserve the shape of a journey. Imagine a tiny compass needle. It aligns itself with the direction of a surrounding magnetic field. Now rotate the field very slowly, allowing the compass to remain aligned with it throughout the process. After moving the field through a closed sequence of directions, return it to exactly the orientation it had at the beginning. The external conditions are now the same. The strength and direction of the magnetic field have returned to their initial values. We might therefore expect the quantum state to return without any change at all, but an additional phase can remain. This is known as the Berry phase. A quantum state accumulates a phase simply because time passes and the system has energy. We can think of this as the dynamical phase. The Berry phase, however, is not determined only by how much time has passed. It depends on the closed path traced by the quantum state through the space created by the changing external conditions. Imagine carrying two clocks on a journey. The first records how long the journey took. This resembles the dynamical phase. The second records not time but the shape of the route. Even if two journeys last equally long and proceed at the same speed, the second clock gives a different reading when the routes enclose different paths. This is the intuition behind geometric phase. The Berry phase cannot be determined from the final conditions alone. Even if the magnetic field and the energy state are identical at the beginning and the end, we still need to know what path was followed in between. The quantum state has returned to its starting point, but the closed loop drawn in parameter space has not become meaningless. Nature compresses the geometry of that loop into the language of phase. This brings us to the idea of holonomy. The word sounds difficult, but its meaning is relatively simple. Transport a direction or a state along a closed path. When it returns to the starting point, compare it with the original. The remaining difference is what we call holonomy. The changed direction of an arrow carried around Earth is a kind of holonomy. The geometric phase remaining in a quantum state after the magnetic field completes a closed cycle can also be understood as holonomy. The Aharonov-Bohm phase revealed when two electron paths recombine is likewise related to a global trace of a gauge connection. Then what is a gauge connection? Imagine two arrows located far apart. To say that they point in the same direction, we need a rule for transporting the orientation of one arrow to the location of the other so that they can be compared. On a flat sheet of paper, that rule seems almost invisible because it is so natural. In curved space, however, the result of the comparison may depend on the path used for the transport. The phase of a quantum state works in a similar way. The phase convention chosen at any single point contains an element of arbitrariness. But to compare states defined at different points, we need a connection rule. A gauge field can be understood as a structure telling us how neighbouring states are to be compared and transported. If we travel around a small closed loop and return with a change, we say that curvature is present. The accumulated difference remaining after a larger closed loop is holonomy. In gauge theory, quantities such as Wilson loops capture these global effects around closed paths. Once again, our view of the world changes. We often imagine that objects exist first and relationships arise afterward. We say that an electron exists, then moves through space, and later interacts with other things. Gauge theory, however, shows that comparison and connection may be necessary, even to define the physical properties of an object. In some cases, the relationship between different points is more directly observable than a value assigned to one isolated point. And this memory of a path is not merely an abstract philosophical idea. If an electron spin is aligned with a magnetic field, and the direction of that field is slowly rotated, a geometric phase can remain in the spin state. Inside a molecule, a path traced by the arrangement of atomic nuclei can leave a geometric trace in the electronic state. In a superconductor, enormous numbers of electrons form a single macroscopic quantum state with a shared phase. The phase accumulated around a superconducting circuit is connected to magnetic flux, and an extremely small phase difference can become a measurable change in electric current. A device known as a squid uses this sensitivity to detect extraordinarily weak magnetic signals. Electrons inside a solid can also acquire a Berry phase as they move through the state space created by a crystal. Topological materials show that the properties of matter depend not only on the kinds of atoms present, but also on the global connection structure of the available quantum states. Holonomy can even become a resource in quantum computing. By controlling a quantum state around a closed path, researchers can design operations that depend more on the overall structure of the path than on every microscopic detail of the motion. The paths remembered by nature can therefore move interference fringes, alter electric currents, determine the conducting properties of matter, and process quantum information. They are real physical resources. But one question remains. What exactly does the universe remember? We should not imagine that nature preserves every moment of every journey like a perfect video recording. Real quantum systems interact constantly with their environments. Air molecules, light, heat, vibration, measuring devices, and countless surrounding degrees of freedom carry away phase information from a quantum state. This is decoherence. As phase information spreads through countless relationships that we do not observe, the clear interference of an individual system disappears. Does this mean that the universe forgets rather than remembers? In one sense, yes. Detailed information about the path of a particle becomes dispersed throughout the environment and is, for all practical purposes, impossible to recover. But not every structure disappears at the same rate. Some information can survive in global forms, such as a phase associated with an entire path, or a topological invariant, even when local details are fragile. The universe may not be a giant archive that stores every scene from the past in one place. It may instead be a system that preserves differences in relationships that remain even after countless events have passed. Human memory and quantum phase are not the same phenomenon, yet they meet in a philosophical question. After detailed information fades, can the trace of a relationship remain? Can the present form of an existence be explained entirely by its present components? Or is the history of its relationships also part of what it is now? At this point, let us turn to the IG, or information gauge perspective. Let me emphasize once again that the Aharonov-Bohm effect, the Berry phase, gauge connections, and holonomy discussed so far are established physics. The information gauge interpretation that follows is a research hypothesis, extending this structure into the domain of physical information. It has not been established that nature contains an additional information gauge field of this kind. The IG perspective begins by refusing to treat information only as an isolated number stored inside an object. Information appears through difference. Hot has meaning in comparison with cold. Direction is defined in relation to other directions. The phase of a quantum state becomes observable only when it is compared with another state or reference. Information that is completely isolated and related to nothing else cannot be physically read or transmitted. IG therefore looks for the physical meaning of information in relationships and connections among states. Particles, quantum states, measuring devices, and environments can be treated as information nodes. The way two nodes distinguish, transform, and compare one another can be represented as an information link. A rule for carrying an informational reference from one point to a neighboring point can then be called an information connection. If transporting this information connection along different paths does not produce the same result, we may interpret information space as having curvature. If a difference remains after returning to the starting point, that difference is information holonomy. From this perspective, the memory of a path is not a secret diary stored inside a particle. It is a relational residue accumulated around a closed loop by the information connections linking the particle, field, environment, preparation device, and measuring device. Let us reconsider the electron interference experiment in the language of IG. An electron state is prepared. Its possible path divides into two branches. Along each branch, the electron evolves through a different spatial connection. The paths finally recombine, and a measuring device reads the relationship between the two states as an interference pattern. The entire process, from preparation and branching to propagation, recombination, and measurement, can be viewed as a closed information loop. Standard electromagnetism already explains the phase difference produced by the magnetic flux inside the coil and by the electromagnetic potential. IG must not claim to replace that explanation. Giving a new name to an already explained effect does not create new physics. For IG to become an independent physical theory, it must predict an additional effect remaining after the standard electromagnetic phase. Geometric phase and environmental decoherence have all been calculated and removed. Imagine, for example, making the spatial electron paths, magnetic field, travel time, energy, and final quantum states identical in two experiments. We change only the order in which the electron state is prepared and becomes correlated with auxiliary systems. If standard quantum mechanics assigns the same final density matrix to both procedures, it predicts the same measurement result. But if the IG information connection has an independent physical degree of freedom, the difference between the information paths traced during preparation might remain as an extremely small residual phase. We could call this preparation path-dependent information holonomy. We might also perform the same information loop in one direction and then in the opposite direction. First, we calculate the phase changes and symmetries predicted by established theory. We then look for a small, reproducible residual deviation from those symmetries. If that residue changes systematically, with the orientation or effective area enclosed by the loop in information space, we may gain a way to distinguish it from ordinary instrumental error. The relationship between decoherence and information holonomy would provide another important test. As environmental noise increases, interference fringes lose visibility. Standard environmental models predict how quickly visibility decreases and how the phase distribution broadens. If information holonomy is a distinct global structure, the loss of interference contrast and the shift of the mean phase might follow different patterns. Both visibility and phase displacement would need to be measured simultaneously, and their correlation carefully examined. A small anomaly in one type of instrument would not be enough. Stronger evidence would appear if the same information loop structure produced a common rule across very different platforms, such as photon and atom interferometers, superconducting circuits, and spin qubits. But an idea does not become true merely because it is intriguing. If a signal resembling an additional phase appears, we must first eliminate far more ordinary causes. A tiny residual magnetic field in the laboratory, slow changes in device temperature, fluctuations in path length, instability in the photon or electron source, and phase noise in the measuring apparatus can all produce false signals. Known Berry phases and dynamical phases must also be removed accurately. Environmental decoherence, post-selection in the measurement process, and biases introduced by data analysis must be checked. If we label every unexpected phase as evidence for an information gauge, we are not doing science. We are merely naming what we have not explained. For the IG hypothesis to be scientific, it must also tell us what would show that it is wrong. If every residual signal can be explained by known gauge fields and environmental noise, the minimal information gauge model is not supported. If changing the path and order of information preparation produces no additional difference, the proposed information holonomy has not been observed. If different experimental platforms fail to reveal a common scaling law, the claim of a universal information connection becomes weaker. For the statement that the universe remembers information to become science, we must also say under what conditions the universe should not remember. Even so, the question raised by this hypothesis is meaningful. Modern physics has already shown that the world is not merely a collection of isolated objects. In quantum entanglement, the correlations between separated systems cannot be reduced to the individual parts alone. In gauge theory, The connection used to compare states at different points lies at the heart of physical law. In general relativity, matter and energy change the geometry of spacetime, and that geometry in turn determines the paths followed by matter. The Aharonov-Bohm effect shows that a global connection can alter an outcome even along a path where no local force acts. The Berry phase shows that the geometry of a journey can remain even when the final conditions are unchanged. Holonomy expresses mathematically that completing a closed journey does not always amount to a perfect reset. IG takes one further step and asks, could the relationships through which information is prepared, transmitted, and compared possess an independent physical structure in addition to the gauge connections of matter and fields? Could the informational connections that we currently treat as background conditions or initial settings actually form a field that changes and responds? Could the curvature and holonomy of that field appear in experiments as tiny residual signals? We do not yet know the answer. But science does not begin only after the answer is known. New research begins when we ask whether two explanations are merely describing the same phenomenon in different words, or whether they make different predictions at some small but measurable point. Let us now return to the traveller with whom we began. After a long journey, he stands before the door of his home. His place of departure and his place of arrival are the same. Yet the house he sees is no longer exactly the house he once knew. Even if the building has not changed, the relationship between the traveller and the house has. An electron can also return to its starting point. The external conditions defining a quantum state can also be restored. Yet a phase may remain in a state transported around a closed loop. It is not the voice of an electron telling the story of its journey. It is the difference revealed when path and connection are finally compared. The memory of the universe may not be an enormous book stored somewhere in space. It may not be a flawless record preserving every detail of every event. It may instead be a slight misalignment that remains because the connections between existences do not vanish completely when a long journey ends. Throughout our lives, we follow countless paths. Some roads are forgotten, and some faces become indistinct. Footprints disappear in the rain, and voices recede into time. But the relationships we form alter the choices of other people. Those choices then create new paths for others. Details may fade, while the changes created by connections continue on a longer journey. Of course, human meaning cannot be reduced to a single quantum phase. Love and loss, memory and identity exist on levels far more complex than that. Yet nature offers us one clear lesson. The present may not be a moment from which the past has been completely erased. It may be a moment in which parts of the paths already travelled appear in compressed form as relationships. Two journeys are not necessarily the same simply because they share a starting point and a destination. Nature does not ask only where something is. Sometimes it also asks which path it followed, what it became connected to, and what closed pattern those connections created. And perhaps a perfect return does not mean going back to the beginning unchanged. Perhaps it means standing at a new beginning while carrying every connection formed along the way. If you found today's journey intriguing, please subscribe and like the video. Together, we will continue following the deeper questions hidden behind the world we think we already understand. This has been ThothSaem's Science Catch.